Welcome back to our heat transfer class, where we're delving deeper into the fascinating world of the Mao energy exchange. This video was made with the support of InnoEnergy. Before studying heat conduction, we recommend you watching the videos on the introduction to heat transfer. The topic of one-dimensional steady-state conduction is divided in several lessons. There is at least one video for each lesson. Let's start with the first one. The lesson about plane walls and radial systems is divided into several parts. Let's start analyzing the heat diffusion equation for conduction heat transfer. The heat diffusion equation is an energy balance per unit of volume inside a solid. It is obtained by applying the Fourier's law to evaluate conduction fluxes. This is the equation of heat diffusion in 3 dimensions with internal heat generation and transient state in Cartesian coordinates. The temperature field is in scalar field, with a given value at each point in the space. In the transient regime without phase change, the solution of the diffusion equation gives the values of the temperatures at each point and their change over time. After knowing the temperature field, we can calculate the heat flux at any point in the solid by applying Fourier's law. The heat diffusion equation may also be expressed in cylindrical coordinates, also in spherical coordinates.
The problem with this equation is its complexity. There are different approaches to obtain the temperature field and, eventually, its evolution over time.
Analytical solutions. Simplifications for one-dimensional steady-state conduction. The hypothesis of one-dimensional steady-state conduction greatly simplifies the heat diffusion equation. For Cartesian coordinates and constant thermal conductivity, the diffusion equation is a second-order differential equation. For solids without internal heat generation, this is the Laplace equation. For cylindrical coordinates, the derivative of the temperature with respect to the radial position is used. The same for spherical coordinates with a different expression of the diffusion equation.
Usually the analytical solution, if it can be found, of an ordinary or partial differential equation can be expressed in terms of known mathematical functions that can be calculated as accurately as we wish for any values of their arguments. For finding analytical solutions, the solid must be homogeneous and isotropic. That is, the properties are the same at any point and in any direction. The thermal conductivity does not depend on temperature. The volumetric heat generation, if any, is uniform. The boundary conditions are such that the heat conduction can be considered one-dimensional. The geometry of the solid is simple. That is, flat, cylindrical or spherical walls. The solution of the mathematical model will predict the real behavior of a physical system as long as these hypotheses are fulfilled.
Temperature distribution and heat transfer rate for one-dimensional steady-state conduction without internal heat generation. For finding the temperature distribution, we must solve the diffusion equation. For a plane wall, without internal heat generation, the diffusion equation takes the form of Laplace equation for temperature. Integrating the Laplace equation, the temperature distribution results a straight line. And the derivative of T is constant, that is, has the same value at any point in the solid. If the temperature of both sides of the wall are respectively T1 and T2, you can find the values of C1 and C2. The temperature derivative is the difference of temperatures divided by the wall thickness L. With the expression of the temperature derivative, you can apply the Fourier's law to find the heat transfer rate. Where AC is the cross-sectional area of the plane wall, which is constant along the x-axis. For cylindrical walls, we use the diffusion equation in cylindrical coordinates that we can integrate twice. If the temperature of both sides of the wall is respectively T1 and T2, the temperature distribution depends on the logarithm of the radius ratio. The temperature derivative is not constant. Applying the Fourier's law for conduction after calculating the temperature derivative versus radius, we find the heat transfer rate that crosses by conduction the cylindrical wall. You can see that in a steady state and without internal heat generation, the heat transfer rate in the radial direction does not depend on the radial position. For spherical walls, we use the diffusion equation in spherical coordinates that we must integrate twice. If the temperature of the inner and the outer surface of the wall are respectively T1 and T2, the temperature distribution is a function of these temperatures and the outer and inner radius. The temperature derivative is not constant. Applying the Fourier's law for conduction after calculating the temperature derivative versus radius, we find the heat transfer rate that crosses by conduction the spherical wall. You can see that in a steady state and without internal heat generation, the heat transfer rate in the radial direction does not depend on the radial position. Summary of the first lesson.
The heat diffusion equation is a complex differential equation in partial derivatives. However, it can be simplified for one-dimensional, steady-state conduction. Even more for solids without internal heat generation and constant thermal conductivity. Solving the simplified diffusion equation and applying two boundary conditions, we can find the temperature profile. After that, applying the Fourier's law, we can find the heat flux and the heat transfer rate in both rectangular and radial coordinates. For plane walls, the temperature distribution is a straight line. For cylindrical walls, the slope of the temperature distribution is not constant. That means that the heat flux changes with the position. However, the heat transfer rate in the radial direction is constant. For spherical walls, like for cylindrical walls, the derivative is not constant. However, the heat flux in the radial direction is independent of the position inside the wall. Keep these expressions in mind for the next video about one-dimensional steady-state conduction.